Welcome to Học Tiếng Anh với Joseph, where we build vocabulary and practice pronunciation through reading. Continuing with The Cat in the Box, today we read story number 45, Pinning Down the Speed of Light. Here you see Hippolyte Fizeau and his collaborator Léon Foucault, and that's the schematic for the apparatus they use to measure the speed of light. Although the speed of light had been known to be finite since the work of Ole Romer, it was only in the second half of the 19th century that the speed was measured with precision. The technique was pioneered by the French physicist Hippolyte Fizeau and refined by his countryman Léon Foucault, who measured a value within 1% of modern measurements in 1862. Fizeau made the first accurate ground-based measurement of the speed of light at the end of the 1840s. He used a rotating metal wheel in which gaps had been cut like the battlements of a castle. A beam of light was fired through a gap in the wheel and along a distance of 5 miles or 8 kilometers between Montmartre and the hilltop of Suresnes, off a mirror and back through the next gap in the tooth wheel. This worked only if the wheel was rotating at just the right speed for the next gap to be in place for the light to get through. By adjusting the speed of the wheel until this worked, Fizeau was able to measure how long it took for light to complete the journey, and thereby get a measure of the speed of light of 194,676 miles or 313,300 kilometers per second, which is within 5% of the modern determination. He also showed that light travels more slowly through water than through air, which is a key prediction of the wave model. The rival particle model predicts that light travels more rapidly in water. Foucault also used an experimental method involving bouncing light beams around, but based on a rotating mirror concept devised by Dominique François Arago. This technique involved light being bounced from a rotating mirror onto a stationary mirror and then back to the rotating mirror. While the light is traveling, the rotating mirror has moved on a little. So the beam of light is deflected by an angle that depends on the distance between the mirrors, the speed of light, and the speed with which the mirror is rotating. By measuring the angle of deflection, Foucault was able to confirm that light travels more slowly in water than in air, and in 1862 to measure the speed of light as 185,172 miles or 298,005 kilometers per second. The modern value is 186,282.397 miles or 299,792.458 kilometers per second. This had far-reaching implications. Exactly at the time Foucault was carrying out these experiments, the Scot James Clerk Maxwell was developing a mathematical theory of electromagnetism, building on from Faraday's work. He found a set of equations that describe all the interactions between electricity and magnetism, which include a mathematical description of electromagnetic waves. The equations automatically included a constant, now labeled c, which is the speed with which these waves travel through the air. This was not something that Maxwell put in. It came out of the calculation without being looked for. That speed was the same as the speed Foucault had measured for light. Maxwell wrote, "This velocity is so nearly that of light that it seems we have strong reason to conclude that light itself, including radiant heat and other radiations, if any, is an electromagnetic disturbance in the form of waves, propagated through the electromagnetic field according to electromagnetic laws." The radiant heat he referred to is, of course, infrared radiation, and the mention of other radiation, if any, proved prophetic. However, the equation contained no mention of the speed of the source of the waves, or the speed of the observer measuring them. They seem to be saying that any observer moving at any speed would measure the same speed for any light waves, whatever the source of those waves. This puzzled many people, and strenuous efforts were made to find differences in the speed of light for beams moving in different directions relative to the moving Earth. These efforts were unsuccessful, proving that Maxwell's equations were right. Albert Einstein, jumping off from those equations and ignoring the experiments, which he may not even have known about at the time, took the discovery at face value and made it the cornerstone of his special theory of relativity, published in 1905. All this is so important that in 1983, instead of measuring the speed of light in terms of the numbers of meters traveled in a second, the meter itself was redefined by the Conférence Générale de Poids et Mesures, General Conference on Weights and Measures, as the length of the path traveled by light in vacuum during a time interval of 1/299,792,458. So it's 299,792,458 of a second, setting the value of the speed of light at 299,792,458 meters per second by definition. So now we know how we come up with a meter. Moving on to the vocabulary section, we practice known to be finite. Finite, not finite. Infinity, but finite. Measured with precision. Measured with precision. Battlements of a castle. Battlements of a castle. Bouncing light beams around. Bouncing light beams around. Bouncing light beams around. Electromagnetism. Electromagnetism. Electromagnetic wave. Electromagnetic. The first one is electromagnetism, stress mag. Second one is electromagnetic waves. So stress net. Electromagnetic waves, electromagnetic disturbance, electromagnetic field, electromagnetic laws. Well, I hope you enjoyed finding out what a meter actually means and how we get it. And thank you for your time, and as usual, I will see you in the next story. Bye for now.